Hello and welcome to Monte Carlo 4. This is going to be the first part of the optimization. So we're looking at three problems today. Our first one is minimizing the following equation. Z equals to x1 to the fourth plus 2x1 squared plus 2x1 x2 plus 4x2 squared. And we have the following constraints. We have 2x1 plus x2 is greater than or equal to 10, and x1 plus 2x2 is greater than or equal to 10. And also x1 and x2 are both greater than or equal to 0. So let's take a look at how we're going to minimize that using Monte Carlo and MATLAB. I'm going to run you through my pseudocode. First, we're going to start by clearing the workbook. We didn't have that function that we're going to minimize called out. We're calling it out as the z variable. So z is equal to that function where x1 and x2 are called out here. So x1 and x2 are going to be initialized as any random number between 0 and 1, as you can see here, this max function. We're going to go down and call out some of the parameters here. So we have our temperature, which is equal to 10,000, our n, which is the iterations, which is the temperature times 10, our sigma, which is defined as 1.8 right now. Our best value goes to infinity, and our count's going to start at 0. So right now we have our main for loop, where I equals 2 to n. We're going to choose any random number between 0 and 30 with these following functions. And then if these constraints are satisfied, we're going to do some simulated annealing with these if statements, which are basically just our constraints. So if both of these are true, we have z candidate is equal to x of 1 of I and x2 of I. And then the same is true for z current, except this is z x1 I minus 1 and x2 I minus 1. So here we have our minimum function here. And if this is greater than or equal to the random number, this is our acceptance criteria to move to I. Then have our else statement here. So if z candidate is not being used, the following is true. X of 1 or x1 of I is equal to x1 of I minus 1, and the same is true for x2. We're going to end that if statement, or that else statement, sorry. And then moving down to if z candidate is less than best, then z candidate is the best value. Our count is equal to itself plus 1, and then you're going to capture the best x values with this function right here. That'll end that if statement. And if neither of these if statements are true, we're going to do nothing. And then after the for loop is ended, we're going to show our best value. I have this inside of MATLAB. We're going to run it, and we're going to see if we can get the answer, which is um, we've done through class is 176.5. We're going to see if we can get that. So I'm going to go up here to run section, and we'll see what we get. Sigma at 1.8. I go over here, and you see the best value is 203.6, which is certainly off by 30 from the optimal answer. So I'm going to play around a little bit with the sigma and see if this changes at all. We'll do 1.85 and we'll run that and see what happens. So after running with 1.85, slightly worse number in terms of getting close to the minimum of 176.5. Really, what you have to do is just play with these parameters. Um, I've seen sometimes where I've gone up to 1.95 and I've changed this, added an extra zero, and I got my best value underneath 200. But it's not a consistent answer. It varies a lot. Minimization problem where we're minimizing the following function here, and our only constraint is that x has to be greater than or equal to 0 and then less than or equal to 31. Pseudocode goes, you'll see a lot of similarities compared to the last one. We'll start always by clearing the previous workspace. You have last time we had z, this time we have f as the function being identified, where x is our only variable. We're going to start by visualizing the original function by plotting it. So that's what it's going to look like here. We're now going to identify the starting position. So all of our initializations, x of 1 is going to be equal to 0. The count's going to equal 0. Z of 1 is going to be the function of x of 1. Um, Z current, I'm sorry, Z candidate of 1 is also going to be equal to 0. Next, we're going to declare hyperparameters similar to what we did last time. We know that T is the temperature, which is 100,000. Our standard deviation is STD, which is 2. Our iterations, we're going to have 100,000. For loop where I is equal to 2 to the number of iterations, which is 100,000. As you can recall, our only constraint is that the x has to be between 0 and 31. We also factor in the minimization here. This is if we had a maximization problem, but here we have our minimization, so this will be commented out actually. Um, so yes, x of I to 31. We have our temperature, which is equal to 90% of the original temperature, as we see 0.90 times T. Z candidate of I is equal to f of x of I. R is going to be defined as just a random number. Our expected value minimization problem is as followed. Looking at expectation of negative Z candidate of I minus Z current of I minus 1 over T. If the expected value is less than R, x of I is going to be equal to itself. You have an else statement here where if it is not, so if it's either greater than or equal to R, then x of I is going to be equal to x of I minus 1. Then we're going to have our end, which is going to end this if else loop statement, sorry. So now we're going to identify that z of I is equal to f of x of 1. And if z current is greater than z current I minus 1, then the count is equal to itself plus 1. We got our best z of c equals z of I minus 1, which is going to obtain our best z value. And then our best x value, which is best x of c, is also equal to x of I minus 1. That's going to end the second if statement. And then we're going to end the for loop. And then we're going to visually display the results through a plot. So we're going to plot our best z and then display our best x value. This is what it looks like when it's implemented into MATLAB. I'm going to go ahead and run this, and we're going to see our answer. Okay, so we have our graphs here. You'll see that once it gets to 20, it levels off. There's 20 over here. And then over in the command window, we have 20.3672. Final and third problem is a traveling salesman problem. We have XY coordinates are equal to rand of 10 to 2. So yeah, we're just going to calculate the shortest tour, and we're going to see it inside of a little graph, and I'll show you what that looks like. Here's our pseudocode, starting by clearing the workspace. Our n is equal to 10, and you'll see the xy coordinates, the rand of 10, 2, that was originally called out by the problem. So we're going to start by plotting the traveling salesman's path. This plot's going to be displayed. The path he's taken is going to show blue lines with red stars to represent each point where he stops and goes. So we now have a for loop. So I is going to be equal to, so these are the iterations. You have 1 to 10, which is n's value. You have an inner for loop, which is basically just calling out the distance matrix, and it's defined by the square root of xy I 1 minus xy of j1 squared plus xy I 2 minus xy j2 squared. So then we got an end, which will end the internal for loop, calling out the distance matrix, and then the end of the external for loop with the iterations. So P is the number of iterations, which in this case is 10,000. This for loop is 1 to 10,000. It's calling out our population. It's identified by random permutations of n. Then we end our for loop there. We then go on to the best value, which goes to infinity, as we see in our other two problems. Our next for loop has iterations going from 1 to p, which is 10,000. Yes. Then we have RT, which is route. This is random permutation for the first genetic random. And then we have route with the circuit back to depot defined here. Our cost return of I is going to equal to the cost function where we have the route, the distance matrix, and n, which is 10. So I have an if statement where if the cost of return of I is less than the best, then it is the best. And then the route best is equal to the route. So the given route we have is the best route. We have two random variables, R1 and R2, which is a random integer of n for each one. Our population replaces the lesser with the best value. And then this line here is going to mutate the best value. And that is the end of our if statement and end of our for loop. Then going down here, we have the best route and the best value. So each of these are going to be displayed in the command window. We have our route equal, so it's displaying the route in the command window, the best one, with the best value and the mutated values. We then have our plot where it's going to show the path of the salesman. Our distance function, function D, where we have the cost function of the route, distance matrix, n. We're initializing the distance at 0. And our final for loop here, we have I equal to 1 to n minus 1. So 1 to 9 iterations there. So our distance d is defined by this following function. So you got d plus distance matrix of the route I, the route of I plus 1. We're going to end our inner for loop and our outer for loop. And that is the end of our pseudocode. Let's take a look at what it looks like in MATLAB. So ignore this random number generator up top. We don't need it for this. We're going to run this, and I'm going to show you the graph as well as the results here on the right side. So this is our figure we're given here, our traveling salesman. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. You have each point identified by the red star. And then over here in the command window, you'll see the best values. So you got your shortest path here. You got your route. And yeah, that solves the traveling salesman problem. I hope you guys enjoyed this video and learned something today through Monte Carlo. Until next time, catch y'all later.